Hello students, welcome to MEC 1321 Engineering Statics. My name is Dr. Stewart, and today we're going to go over section 7.3 from the book titled Relationships Between Distributed Loads, Shear, and Moment Diagrams. So in the previous video, we learned how to use the method of sections in order to create shear and moment diagrams. We learned that we can take a beam and do a series of sections across that beam in order to determine the functions that describe the internal shear and moments within that relevant section. Today we're going to learn about some special relationships that exist will allow us to more quickly determine the functions of the shear and moment functions that develop within a body. So let's go ahead and get started here. If a beam is subject to several concentrated forces, coupled moments, and distributed loads, then the shear and moment diagrams can be very difficult to find. In those cases, in the cases where there's a lot of loads that are applied to a beam, it would require that we do that we cut multiple sections through the beam to take into account each of these loads, and that for each of those sections we apply our equations of equilibrium and solve for the functions that describe those sections. So it can take a significant amount of time to solve a problem. So in this section we're going to learn a new method based on differential relationships that exist between load, shear, and moment in order to more quickly solve for the shear and moment diagrams. So let's consider a beam that has a complex state of applied load. Let's look at this beam here. We've got distributed load applied to it, we've got concentrated forces, and we have coupled moments applied to it. And it's clear that if we wanted to use the method of sections, that we would have to do quite a few sections in order to craft our shear diagram. We'd have to do a section here, a section here, a section here, a section here, and a section there. We'd have to do 1, 2, 3, 4, 5 sections, and then for each of those 5 sections, calculate apply the equations of equilibrium for each of those sections in order to craft our shear and moment diagrams. And that's just not feasible if you were to try to solve this problem on an exam. So let's try to take a new approach. Let's take an approach where we look at differential elements or differential segments of a beam and try to identify some relationships that we can use towards solving these problems. So let us take a small segment or small increment, delta x, and analyze it as follows. And let's note that it's not subject to a concentrated force or a coupled moment. So let's take a small segment where it's just subject to a distributed load over that segment. And let's see what we can do here. So the distributed load, Wx, over this small distance delta x can be replaced with a differential concentrated force, right? If we have a distributed load, we can turn that load into a single resultant. So we're going to create a differential resultant, or delta F, which is equal to the distributed load times the distance, the delta x. Now, if we find, we've calculated this delta F value, and this delta F value is going to be found at some distance relative to the point of interest, point O. Let's call that distance as K. Let's call that distance as a value of K. Right? So K is a factor value, where if K is 0, then the position is 0, and if K is 1, then the position is delta x. Noting that, if we look at K, and if we had some uniform distributed load that was constant, then it would be clear that K is equal to 1/2 in that type of situation. So we're able to take this section of the beam, make the differential length, the delta x, associate with this resultant force that is found at some distance K. So, with this type of knowledge, let's go ahead and try to describe a relationship between our applied load, or our applied distributed load, and the shear force that develops within the body. So let's apply the force equilibrium equation to this segment. And let's use the sum of the forces in the y direction, because that's the direction of interest, where the sum of the forces in the y direction is going to be equal to 0. Notice that in this section, we add our shear force and our moment forces, these internal forces that develop within the member. If we apply the sum of the forces in the y direction, then we'll find the resulting equation, that the shear force plus the distributed load times the increment to x minus the shear force plus the change in the shear force is equal to 0. Then if we, noting this relationship and canceling out the like terms, we find that the change in the shear force is going to be equal to the distributed load times the length of the differential element, the change in x. Now, if we are to divide both sides of this equation by the delta x, and if delta x is something that is greater than 0, then we'll find, if delta x approaches 0, it approaches a very small value, then we'll find that the change in the shear force over the distance is going to be equal to the derivative of the shear force with respect to x, position x. And that is all equal to the value of this distributed load. From this, we find that we've developed an equation, a differential equation, which describes the relationship between the shear force and the distributed load, where the left-hand side is equal to the slope of the shear diagram, and the right-hand side is equal to the intensity of the distributed load at the position of interest x. Now, if we were to rewrite this above equation into the following form, and then perform integration between 2 points of interest along the length of the beam, then we'll find that the change in the shear force is going to be equal to the integral of the distributed load with respect to x, where the left-hand side of the equation is the change in the shear diagram, and the right-hand side is equal to the area under the loading curve. Now let's look at the relationship between the shear diagram and the moment. So again, let's take this same diagram where we have a differential distance x. We have some distributed load that we can describe as a singular resultant delta F, and we have the internal forces that develop on the left and right hand side of this section. Now let's apply the moment equilibrium equation, where we want to do the sum of the moments about point O is equal to 0. When we apply this equilibrium equation, we're able to put our internal forces as well as our known forces due to the distributed load, and we develop the following equation, where the internal moment M plus the change in moment minus, in brackets, the distributed load times the length of the section of the beam times K, which is a factor of the position of the distributed load times delta x, minus the shear force, the internal shear force times the delta x minus the moment is equal to 0. So we're simply taking everything in our diagram and applying it in terms of the sum of the moments about point O. Once we've done that, we can cancel out the like terms, and we'll find that the change in moment is equal to the internal shear force times the distance plus the K factor times the distributed load times the distance squared, or the length of the section squared. Now, if we are to take both sides of this equation and divide by the distance delta x, and as x approaches 0, we'll find the following relationship, that the change in the moment divided by the change in length, or the differential moment with respect to the change in length, is going to be equal to the shear force plus k times wx times delta x. We're noting that as the delta x approaches 0, this secondary term becomes very small and becomes 0. From that, we find the following equation, that the derivative of the moment with respect to x is going to be equal to the shear force function, such that the left-hand side of this equation is the slope of the moment diagram, and the right-hand side of the equation is the shear force function with respect to x. Now, an interesting property of this equation is that we can, if we think about this equation closely, we can find the points at which the moment within a function is maximized, where the maximum magnitude, the maximum magnitude of the moment is going to occur when the derivative of the moment with respect to x is equal to 0. And this is because the maximum moment is going to occur when the shear forces are equal to 0. Now, if we were to take the above equation, take this equation here, and rearrange it and perform integration from across 2 points of the beam, then we'll find the following equation, where the change in the moment is going to be equal to the integral of the shear function with respect to x, where the left-hand side of the equation is the change in the moment diagram, and the right-hand side of the equation is the area under the shear diagram. So we've been able to find and establish a relationship between the shear diagram and the moment diagram. So now let's kind of go into some peculiar things that happen with these equations. So the distributed load shear and the distributed load shear moment relationships that we just found, those two relationships are not valid at points where we have concentrated forces or we have coupled moments acting. So if we find some concentrated force or some coupled moment, we can't use those two equations. Those equations are going to work only for our conditions where we have a distributed load. So the cases where we have concentrated forces and coupled moment acting are special cases. And these two special cases create discontinuities in the shear and moment diagrams, and as a result, they each deserve to be treated separately. And what that means is, and when I say discontinuities, it means that concentrated forces and coupled moments create discontinuous jumps, like just jumps in the value of the shear and moment diagrams. They're not smooth transitions. They're instantaneous changes in the shear and moment diagrams. And so we need special equations to study them. So let's focus on a concentrated force. If we were to take a differential element of a beam where we found a concentrated force, then we would have the following, then we could create the following free body diagram, where we have our concentrated force, we have some differential distance, and then we have the internal forces that appear to the left and to the right hand side of the section. The free body diagram of a segment where a concentrated force is observed. We can apply our force equilibrium and it'll give us the following equation, where the change in the shear diagram is going to be equal to the magnitude of the concentrated force. Since the change in the shear is positive, the shear diagram will jump upwards when the force acts upward on the beam. Okay? So it's important for us to be able to very readily see that it's an instantaneous jump upwards if the shear force is positive. Now let's look at the example of a coupled moment. If we have a segment of a beam where a coupled moment is observed, we can apply the moment equilibrium equation. And we'll find that the change in the moment is going to be equal to the magnitude of the coupled moment that is applied in the body. So the change in the moment is positive in this case, so the moment diagram will jump upwards if the moment is clockwise, right? Remember that the sense when we're doing our shear and moment diagrams is based on clockwise for the moment being positive. Likewise, if the jump is downward and negative if the moment is counterclockwise. So it's important for us to remember the concave upward, concave downward influences of these shear and moment diagrams. So there's a couple of important points that the book wants to stress in this blue section for the notes. So let's kind of go over some of these important points. The slope of the shear diagram at a point is equal to the intensity of the distributed loading, where the positive distributed load is upwards and has a relationship of the change in the shear, the derivative of the shear with respect to x is equal to the value of the distributed load. If a concentrated force acts upward on the beam, then the shear force will jump upward at the same amount. So there will be an instantaneous change in our shear diagram due to that concentrated force. The change in the shear, or delta V, between 2 points is equal to the area under the distributed loading curve between those 2 points. The slope of the moment diagram at a point is equal to the shear. So the derivative of the moment with respect to x is equal to the shear value, the value of the shear at that point. The change in the moment, or delta M, between 2 points is equal to the area under the shear diagram between 2 points. So we can find the change in the moment by looking at our shear diagram and finding the area under the curve. If a clockwise coupled moment acts on the beam, the shear force will not be affected. However, the moment diagram will have a jump upwards equal to the amount of that moment. So if we have a coupled moment acting, we have an instantaneous jump in our moment diagram, but the coupled moment does not influence or does not affect our shear diagram. Points of zero shear force represent points of maximum or minimum moment, since the change or the derivative of moment with respect to x becomes equal to 0. So the absolute maximum value can be found where the shear force is equal to 0. Because two integrations of the distributed load are involved to first determine the change in the shear and then determine the change in the moment, then if the loading curve or if the distributed load is a polynomial of degree n, then the shear function will be a curve of degree n plus 1, and the moment function will be a curve of degree n plus 2. Okay? So these are quite a few important points that are made about using these equations that describe the relationship between load, shear, and moment. Now clearly, after going over this video, you're not going to have a truly full understanding of how to implement and apply these equations. So it's very important for you to try to go through some of the examples from the book, as well as the fundamental problems, to get yourself comfortable with applying these equations. Notice that in these equations, it requires for you to either do some differentiation or integration in order to solve for the shear and moment diagrams. It's very important for you to review your calculus, to brush up on differentiation and integration in order for you to do well in this section of the book. There will be a problem like this on the exam, so it's very important for you to be comfortable with creating your shear and moment diagrams. With that said, you should review this section of the book. Definitely read it, because this section is a bit tricky, and there are some small details that I did not go over in the video due to time. So make sure that you spend the time to read the book and do some examples. Of course, come prepared for a quiz, which will be an exam style or quality of problem, and come prepared and bring your questions if you do have them. Thank you for taking the time to watch this video. I'm Dr. Stewart, and I'll see you guys in class.